multi-band rectina. So this is the triple band energy harvester, and they have used 3 band 575, 900, and they have multi-voltage multiplier, different stage to improve the efficiency. They have used without matching and with matching. You can see here difference. If you match rectifier, you will get wide bandwidth with the variation of the different power level. If you have only one match and only one input power match, so you will get only maximum at the only one input power level. If you have match,
matching it with simple low pass network. With that one only we can achieve one frequency. Triple band.
if you go in this paper, they have a matching design also. You can check this paper. It's just showing the what is the difference between match and without match. This is the without match, and this is the with match. So they have compared with a different band, and this is just DC combining. You can see here, if I increase the number of stage of rectifier, so if you look this one, not big effect, or even like decreasing with number of only the single or non-match. Oh, this is the non-match. You can see some effect up to 4, 5, up to 5 stage is increasing. If you look this one, efficiency increasing up to 5, and then again decreasing. So this is the optimum for the low frequency. If you have high frequency, it's different. It depends on the frequency, efficiency. And if you look the match case, no effect. If you're using 1 or 2 up to 12, not big difference. Almost same. And this is the GSM band. And for this one, non-match can get the maximum around 3 scale. But you can see again, in match condition, no effect of the number of stages. You have 1 or 2, 3.
If we increase the number of stages, efficiency drop a little bit because we are adding the more diodes.
Yeah, for this case, slightly decrease. You can see here. With the match scale, you will have perfect match. And the non-match is decreasing. And for higher frequency, you can see this is the drastical change. Low frequency have low effect, and high frequency have more effect because loss increase. In the you have the big circuit, so you have loss and microscope. So number of stage depend also the frequency, and they have compared with what is the effect of if you are combining 3 frequency and 1 frequency. You can see here this is the individual 43%, and if you combine, you can get the 68% efficiency. And the difference between the individual and the 3 system is around 58%. This is that some their finding. Voltage multiplier circuit must be used in the energy harvesting because often the voltage is very low in scale. Voltage and the harvested power type depend on the input RF signal level. Impedance matching is important for energy rectina to get the efficiency. Low level input signal for RF energy harvesting, the impedance matching must be used. The impedance matching is very important. You can see here. And this is the multi-band stack RF energy harvester. This is the wideband antenna. This is what it is. This is the only one design RF band pass filter for an RF broadband. This is the wideband antenna. They designed the broadband filter here because this is the wideband antenna. And for this case, they designed the multi-band filter. And this the they proposed architecture. They use the wideband antenna with different band pass. This is the band pass filter, different band pass filter with different frequency, three different frequency, and they connect with rectifier and then combine DC. And this the rectifier topologies, series voltage, and they have combined everything and fabricated and measured. This is the S11 for 4 band, GSM 900 and 1.8 gigahertz, 2.1 and Wi-Fi band. And it's very good reflection coefficient of the rectifier harvester, RF harvester combined with the antenna. And this is the efficiency. If you combine all band, all four band, you can achieve the higher efficiency. And this is just 1 and combine 2 and 3 and 4. If you have a multiple band harvester, you can increase the output voltage or efficiency. This is the antenna, dipole antenna, wideband. You can see, and this antenna can cover all band from 0.8 to 2.4. 0.8 to 2.4 with a good gain. They use this antenna in this rectifier to keep all band. And this is the power input in TBM, and this is the RF to DC conversion with different band or different combination. This is the only one frequency, two frequency, three frequency, four frequency. You can see the difference. If you have a 4 band, you can combine and you can get the around 80% 0 dBm. But this is the other way to improve the efficiency. You can add the multiple frequency band and use either multiple antenna or wideband antenna. You can achieve the 80% band, 80% efficiency is very good. This is the gain of the antenna, very consistent with frequency from 600 to 2.6, 2.78. And this is the output voltage. This is the all band combined band, and this is the separate. You can see the drastic change. If the distance from the source is 50 centimeter, you can achieve the 4 voltage. And if you change the distance, voltage drop, output voltage drop. For sensor application, this is the minimum voltage. So you can use for this retina for sensor application. And they have a huge. This is the transmitter, and they put the 50 meter away from the source, and they put the voltage meter, and you can see here DC output harvested power, and this is the efficiency. Around more than 80% efficiency. And this is the harvested power microwatt. And this graph shows the output power with distance and power summation error. You can see the output power decrease with the distance. If you have 50 centimeter, you can get the maximum power. And this is the comparison with other paper. This is the design, and this is the for this the proposed one, multi-band, and this is the single band, wide band, and they compare. You can see here power efficiency 15% at minus 20 dB, and power 45%. This is the outdoor efficiency, and this is the output DC output voltage, and this is the efficiency RF to DC conversion. What is the main they can cover 4 band, but efficiency, if you look at efficiency, is not high compared to the other. I think you have to go through the paper to get the information. And they have compared the RF to DC power with changing the input power. But this is a different source of the paper. This is the point you can see. They can, for conclusion, they can achieve almost same DC RF to DC conversion efficiency with other paper. This is the 31. They have reference in the paper. And this is the RF to DC conversion efficiency with variation of the input power. And this is the reference one, and this is the proposed one. You can see the proposed retina efficiency increased with increasing the input power up to minus 4 dB. This is the claim, their claim. Compared to this paper, this paper 14, their efficiency increasing with increasing the input power. This is the ultra wideband multi-band retina on paper substrate. They use the paper substrate to design the multi-band retina. This is the antenna structure, wideband antenna structure. Then cover this antenna can cover multi-band 1, 2, 3, 4. And this is the port, feeding port. This is the feeding port here. This is the ground plane, and this is the top. This is 2 feeding port. One here, one here. And this is the S parameter. You can see one band here, simulated and experimental. And this is the gain in all four bands. Antenna 1, antenna 2. This is the one port is antenna 1 and this is the antenna 2. This is the two separate antennas. And they have designed the rectifier for this antenna. And this is the two well, port 1, port 2. And this is the S parameter and S22. Port, this is the two port. You have one S11 and S22 port and port 2 and this is the port. This is the port 2 and this is the port 1. And this is the output voltage for port 1 versus frequency. But this is the band here around 900 and maximum voltage around 1.3 with different power level have different voltage. And this is the for port 2 and port 2 can cover 3 band and this is the different power level. If you have 0 dBm, you can achieve around 1.2 volt. And this is the rectifier RF to DC conversion and with different power level. You can see here maximum efficiency around 60%. And for the other band, for other port, the maximum efficiency around 48%. And this is the combined ones of both band. Final rectifier, this red one. There's a different no input filter. What it is? No input, no output, no input output, no substrate loss. If you know substrate loss, then you have the highest RF to DC conversion efficiency. No input output. What is meaning?
Interaction. They have written interaction.
Interaction, okay. Means no interaction. One is 50 ohm load, other is the active. No output interaction. You can read, I think, paper. This is a very long paper, MTT paper. This is the simulated RF to DC conversion efficiency of rectifier to with and without input transmission lines. So it's minus 10, 15 dB. At minus 15 dB is the rectifier 2. And this is the multi-tone test measured output DC voltage versus available power, input power. This is the input power and this is the DC output voltage with different band, 900, 1.8, 2.6. And this is the combined one. And this one is the combined with the 3 band. You can see here difference because in last paper, if you combine more band, you can get the more voltage. Here is the little bit difference, and this is the one color here. And Oh, this one is the only one 900, and this one is the 900 plus 180, 1.8, and this red one is the 900 plus 2.6, and blue, this one is the 1.8 gigahertz to 2.6. Means the lower frequency is the highest one, only single frequency. This is the rectifier, multi-band rectifier RF to DC conversion efficiency with load. This different load with conversion efficiency, and this is the measurement. The 900 is the maximum, and the other frequency have lower. And this is the major output DC voltage for RF change the input power. The DC voltage is changed around this is 0 dBm. You can get the maximum one. For random source is this one, and you can see here maximum for the 900 band. The gain at 900 very low. That's still getting very good at it. And they have fabricated and measured, and this is the measurement setup, and you can see here output voltage with power density at around 10 microwatt per centimeter. You can get maximum power for 900, and this is the 1.8, and this is the 2.6. And this is the test of retina level. RF DC conversion efficiency with power density. This is the efficiency, and maximum efficiency of 900 band is around 55 at this power level, and other two band is almost same. And this is the retina performance with different banding. They use to bend the texture, and you can see not big difference. If you change the radius like this, not so big difference, almost same. So they have design on the paper substrate. If you bend, so the voltage not changing much. So you can use the any conformal shape based device. And this is the comparison table. You can see this the frequency, different frequency band, and at this power level, major efficiency is 70, output voltage 1.02, and area is only 11 by 11 centimeters square, and copper tape, and loss tangent 0.05. If you compare this paper and only one band, this work is have compared to this, and same paper substrate. And they have tested on the one is the on if you mobile on calling, you can have some voltage, you can harvest the power. And microwave oven also have 2.4, and you can get the power there. So this the just a simple test. You can use the paper and paper substrate and copper tape, just cut, design on 2.4 frequency. You can use the microwave, and you have voltmeter, just put. No need to buy anything, just simple project for us. can use any paper or any plastic or transparent, and transparent. You can use the plastic substrate also. Just put on microwave, you can check how much power you can get. So this kind of work you can use in your study. It's good to get the confidence. And very simple, very cheap. You have copper tape, just cut and just design if you want to use this one 2.4 and fold this one 900 or 1.8. And if you calling, you have the higher power. If you call on mobile or you are SIM call, you have higher power, you can get some voltage. This is just testing for project. And this is the tri-band, and just like a monopole, they have one band here using CRLS. From this gap, you can see here, you can get the series capacitance, or from this one, you can get the inductance, shunt inductance. So this one you can see can call the composite right hand, left hand. Because this patch and this is like a patch, normal patch, you can get the capacitance, inductance, and this is the just negative. They call the composite right, left hand. Left hand you can get from this capacitance and this inductance. So one band, this one band from this, and one band from this. They designed tri-band with sizes were not very small size, not big size, 40 mm by 90, and for three different bands, 900, 1.9, and 2.4. And this is the matching circuit. Oh no, this is this diagram, CRLL. This is the right hand, and this is the left hand. You can see this the capacitance. You can generate from here. This is the capacitance, series capacitance, and you can get from. So you can design the CRL based structure line. And the monopole, and this monopole is 2.4, and CRL and this one is the 2.4, and CRL should be this one, because CRL is very small, compact, and the other band is very small. So you can design tri-band. Yes, CRL one this. And this is the rectifier, the multi-stage rectifier for tri-band 1T. And this is the S11 for rectifier. And this one is the result for different band. You can see the lower band is the highest efficient compared to the other two bands. And they have also tested with a different combination, only one band on, and the harvested voltage is 112.6 millivolt, and harvested power 1.06. If all on, can get the highest one, 7.06. So you have multiple source, you can get the more power, more efficient rectifier or harvester. If you can harvest 2-3 band, you can get the more voltage, output voltage, and you can charge your mobile or the temperature sensor. And this is a very interesting work. Recent work, only I think they presented in last year APS. And this is the Ramaswamy work. They're trying to get signal from all directions. You have a radome like this, and you can put the dipole in all directions, and you can receive. This is the multi-band. So you can see here the height of the dipole is different for different bands. And you have plug here, you can get the power from there. Because inside you can put the rectifier. This is like just like a power bank. You can get the power free of power without. And if you have very high, because this one can receive all direction, so you can get the more power. You can put in your roof, and you can get the power from free of cost. If you have the tower is very close to your house, you can get no need to get electricity. Just put 2, 3 this one you can get. At least you can on the light. So this is just a 2-page paper, not much information. They just propose maybe this year or next year you will get some transaction or proposal. And all angle, all polarized wave you can receive. Because last year we are also thinking this like this structure, but this guy published first. So and this is the return loss of the triple band, and they have compared with the HFSS and FICO other software, and you can see the both software showing same result. It means it's okay. So this is the only one unit, and the radius of this is around 15 centimeter. You can see the different band or different lengths have different band. And this is the radiation pattern of only one unit, means only this one. They have many, all. But this one can increase the aperture size. You can get the more power. If you have large aperture, you can get the more power. If you have more power, you can get the more. If you design properly the rectifier topology, you can get the higher power. Just put 2, 3 in your group and get power. Free power. And this you can see the omnidirectional, perfect omnidirection radiation pattern, and this is the standard dipole and radiation pattern in YZ and XZ range. The design like this something. And this is also very good paper. They want to high gain in all directions. This is the just like a sectorized antenna. We have sectorized antenna, you can get power from all. And using the Butler matrix, you can change the beam. If you can change the beam in this direction using the Butler matrix, and you have all around this sector, so you can cover this whole area and with high gain. You can see here around 10 dB gain. And if you have like this in all direction, this one, this thing, so you can cover all directions. The idea is isotropic antenna, design isotropic antenna. For energy harvesting, isotropic antenna is the best. So this, if this antenna work, can cover all direction with high gain. Because if you want to cover all direction with one antenna, the gain will drop around 1 dB, 2 dB you can get. But if you want to high gain, you have to use the sectorized antenna to get the high gain. Otherwise, you will not get in all directions same gain. And there the frequency on same frequency, 2.4 target frequency. This is the return loss, reflection coefficient, isolation. S11, S21, S22. And this is the different, but these are four port. 1, 2, 3, 4, 5. There's a many antenna. 1, 2, 3, 4, 5. But they have many ports. So we have to check all port. Reflection coefficient, transmission coefficient should be what it is, the S11, S21, S2, S11, S21, S22, S1. They have many port, many combinations. The simulated one. And this is the Butler matrix. And they have designed Butler matrix and fabricated and tested only one section. This section only, one section. And Butler matrix, you can define the phase based on the direction. You want this direction, you can change the. You can, based on the direction, you can change the phase of this line. You can change the beam. Design. If you want the beam this direction, you can change the phase of this Butler matrix. You will get the beam. So their concept is to design the very close, get the all directions same beam. If you on all this sector, you will get the cover like this all direction. So you can receive the high power in all directions. But the gain is higher, around 10 dB. So this is the other way to get the high power. Either multiple antenna or dipole antenna. Have to increase the aperture. And this is the fabricated one, only one section. You can see they can achieve the higher gain with almost only said with high gain. This is the challenging part. So only sectorize to get wider beam. Otherwise, you cannot achieve. This is another antenna, millimeter wave, 24 gigahertz, and this is the SIW. You know SIW? Because the waveguide, they convert to the waveguide in the planar form. Just decrease. you have waveguide, rectangular waveguide, they convert to in PCB, this is the substrate, and then they change the wall with metallic via. So you can reduce this height and almost same performance. So this is the waveguide, SIW, substrate integrated waveguide. So they have used the substrate integrated waveguide antenna for energy harvesting, and at 2040 kilohertz, you can see there the S11 measured and simulated, and these are the dimensions of this. This is the test slot antenna, excitation is here. This is the up to here waveguide, and this is the microstrip, and this is the taper for matching, and this is the microstrip line. And this is the rectifier, and here they've added rectifier, and they have measured RF to DC efficiency, simulated and measured, and around 15% they can achieve, because this is the high frequency. If you have high frequency, you have higher loss. So the efficiency only 15%.
Sir, the table structures, to what extent they help or better the performance?
No, for if you design microstrip based antenna on higher frequency, you have loss. So for high frequency, the waveguide or the SIW based antenna is good, no loss.
Because I guess practically it is very difficult to implement the via structures.
This is a very expensive fabrication, but the performance is very good.
For high frequency range.
Yes, because this one don't have the copper loss. Wave going inside, they like a waveguide. And this is the, they have changed the scanning angle. And you can see that at the port side, you can get the maximum voltage. But it's the narrow beam. Beam is not here. It's narrow beam. So you just get the only port side. This is the angle. But the radiation pattern of this antenna should be like this. So, like this. So only this one performance. Array configuration or enhance the RF power harvesting. They use the two. One is the RF combining circuit, and other is the DC combining. And they fabricated both and measured and compared. And you can see here it is sample, measured and calculated DC power harvested by. Here, this is the DC power combining. One is the AC power combining. So DC power combining is better for minus 30 to plus 30. If you look the AC combining, better for offset. And this is the graph to compare the both technique, DC combining and RF combining. And what it is, retina topology indicator means this RF combining divided by DC combining. You can see here, RTI is good in this region up to 22. After that, DC combining. This is the ratio of the RF combining and the DC combining. So it is the more than 0. It means the RF combining is better for near the board side, only this side, and DC combining of both side. You can see here the DC combining is better. So for array antenna, DC combining better of both side. You change a little bit to your harvester, then DC combining better. You can get the good performance in this. And this is the novel 6-band dual circular polarized antenna using improved impedance matching technique. Harvesting. This is the recent paper. They use the voltage doubler and with 6-band combined two and one antenna. And this is the this is the matching circuit. And this is the matching circuit. And this is the rectifier. Six-band rectifier. And you can see here measured and simulated RF to DC conversion efficiency of the rectifier. With the 6-band 1, 2, 3, 4, 5, 6. So you can use this topology. You have the 4-band. You can use this one. And you can see the up to here. All band can achieve more than 40% efficiency. And this is the dust reflection coefficient for measured for different load, 3 input level for load resistance of 25. They have different input power, 10, minus 10 dBm, minus 20 dBm, minus 30 dBm. And lower 3-band and the higher 3-band. And this is the simulated RF to DC conversion efficiency of the proposed rectifier for different load. This different load have different efficiency. Minus 40 kilo ohm have higher for lower band, but lower in the other band that I do. And this is the measured and simulated reflection coefficient of the rectifier at 2.25 kilo ohm. And this is the conversion efficiency, simulated conversion efficiency of the rectifier with input power with different load. At 10 kilo ohm, we can get the highest one. And this is the measured and simulated with 2-band, 900 and 1.8. Combined one and single one. You can see here, this is the single 900 band, and the highest one is the, you can combine all 6 band. So you can get the around 80% efficiency. This is just for rectifier. This is the rectifier measured and simulated reflection coefficient with different load, and this is the conversion efficiency with different load with all band. And they have designed wide band antenna with rectifier. This is the antenna, what type, and then change the low periodic, again change one. You can see here the very wide band, and they compare all four proposed one. And you can see here this one can cover from 0.6 to 2.5. So you can use this antenna for wide band or multi-band antenna, when multi-band antenna design. This very long paper, and this is the axle ratio with all 6 band, 1, 2, 3, 4, 5, 6. And this is the current distribution with different frequency. This is the major receive power versus frequency and major output voltage, the proposed antenna. The outdoor, this is the outdoor, and this one indoor. You can see the 1, 2, 3, 4. But that depend on the band in the outdoor, you receive different band. Because in the outdoor, the Wi-Fi don't have, so you cannot receive. Only you can receive only 4. And this is the realized gain of the antenna only with frequency. The gain is okay, I think more than 3 dB in all band. This is the efficiency outdoor and indoor. You can see here outdoor efficiency is higher compared to indoor. What is the band? Because the outdoor have the more band compared to the more power. But if you measure here, outside is different. It depends on distance. And this is the comparison of different work with their work with the 6 band and dual polarized and can achieve the 80% efficiency and with load of 10 to 55 what is this, and the input power is 96 microwatt. Any questions?
And then SIW technique that we use for low frequency applications like
Low frequency is the size problem. You have to have your W should be lambda by 2. Because you're using the 2.4, 1.2, the size is increased. This size. For high frequency, the size is no problem. The wavelength is very low.
small.
Yes. If you want to filter, can use the folded SIW. You can reduce half, or you can use the half mode SIW. Also, so you can just reduce the half size. Just cut here. You can use the half.
Particle.
Yeah. Just cut like this. Like lambda by 4. For your project is very good. And for this technology very good. Just to follow one. And you can design one antenna like this. One antenna enough for you. 4 band can go. What is the highest band you are band? You can see. Yeah, then you can go. Just design simple and test.
They got also like the outdoor condition.
No, this is the error bar. I think it's not the exact one. Why they got the higher?
Outdoor condition also receive.
If you look here, the outdoor is the higher power. Compare minus around minus 46, and this is a 20, 22 minus 22. Big difference.
I think they have taken reading here maybe from base.
Yeah. Distance, it depends on distance. So you can see here, outdoor is the large.
Then
With a big difference. Indoor, I think all band have below minus 35, and this one 35 is more than 35 or
more than 20. But
35.
this 4G LTE, its frequency is 2.3 now.
Band
LTE frequency is 2.3.
800 also.
No, sir.
Higher. And you can see also here the higher voltage in multimeter. Maybe the outdoor is close to the base station. Yeah, that's why. Yeah. Any other?
As you are repeatedly telling that not to believe on the radiation box while designing in HFSS. When we design, we usually keep the radiation box more or less lambda by 2 distance apart.
It depends on frequency also. Yeah, lambda by.
So, like, is there any particular reason that to maintain that much distance?
No, it's, you have to check. It depends on structure and your structure thickness.
Like, I have seen that in some cases, if I keep my radiation box small, then I'm obtaining good result. But when I increase the dimension,
Then you have to optimize the radiation box based on your good result.
like how that can be practically.
No, first you have to check the experimental problem. Then you can have the knowledge. Otherwise, if you add 2 lambda, 1.5 lambda, it's different.
For every dimension, the results are different. But
That's why the problem in HFSS.
Now the problem is to believe in.
That's why if you know two software, then you have to compare with two software like this. If you two software same, then your result is okay. Replicate and check. Only simulation. Yes. Simulation change. If you change the matching, other thing, the result always change. Otherwise, you have to check the conversion. You know the conversion and the method of movement or something. Conversion rate condition. Then you can get the good result. You have to know the method, whatever the method they use, finite element method. You have to know how the conversion can get. Otherwise, you will not get the result, good result. You have to compare two software, either two software or you fabricate it. Otherwise, you have to know the method. Finite element method.
I have a doubt regarding the gain. When we are getting indication on curve, we will get the better resonance. I mean, maximum D. Always we will get the maximum gain at this resonance point only.
Means you have resonance. You have resonance like this.
Yes, sir. If let this resonance at 4 gigahertz.
Okay.
Get peak gain at 4 gigahertz only.
Because reflection. If you have good matching, no reflection.
But the gain what is we are checking in HFSS or CST, that gain is radiation gain or antenna gain. Antenna gain that one.
Radiation gain means
Radiation efficiency. From that we can calculate something.
no. You can calculate efficiency with directivity. If you are same, you can get 1.
Sometimes there is also people who are showing that radiation efficiency.
Efficiency means the mismatch loss. We are not considering this loss. Efficiency means divided by power input or irradiated divided power input.
Power input is the power input to the antenna.
If you want the total efficiency, irradiated and T in and minus TC copper loss minus and what the T and other loss, surface wave loss. We have to consider all. The gain means you are considering everything in measured gain. In simulation, realized gain consider everything. One is the light gain, and realized gain means actual gain. Matching software, if you not match, the gain will drop. The other gain not dropping. Yeah. It means the IEEE gain not considering the matching. In IEEE gain, you will get here very good gain.
Yes.
Matching is very important. We bring the power to and radius to antenna. Radius. Some power reflected back. Sometimes you can find in simulation you are getting the gain increasing with frequency. Like this, and your gain is increasing. So,
Like this.
yeah. The real gain, realized gain. And if you check the IEEE gain, sometimes is increasing. No drop. You are not getting like this.
Then if the antenna is giving negative gain, negative dB,
Mm.
can we propose
And negative gain means at both sides.
this?
Yes, you can get the negative gain. Radiation pattern like this. Okay, means this is the negative both side. Yeah, small size. You have
Or which application that can?
for if you have a very small device, means a smart meter. Nowadays the meter, the frequency they use very low. This like minus 6 dB. Transmit the data from the meter and the center of the smart meter. They can receive wirelessly. You need to go home to check the meter. Came down and then just check the data by meter. Reader. You have a very tall building and there's you can get the data all by wireless. We have done this project, but now they are planning to change all meter. So you have to go all very tall building, go every house. Wirelessly you can get the data at one place, all building, with certain distance, around 200 meters. So the antenna size is very small, that could be around 6 or minus 5. But we have the directional gain. We have been and the meter like this, we will do directional. We have to have a knowledge. Sometimes we getting negative result, negative gain result means this antenna not working. But if you know the application, then you can write. Otherwise, you thinking this is useless. For antenna designer, radiation pattern, gain, directivity, you should know basics. And application also, system application also, then you can design application. For energy harvesting, you have to propose like this. Will get because here the TV tower very close. And design. Any other? DR antenna is like different shape DR. Wideband DR can cover wide. Then okay. We do like research like this. We survey whatever in this direction what have been done. Then we do presentation like this and find out the problem and solve the problem. This is the way. First we have to survey. Refer in the area, read and present to someone and discuss the problem. This is the way. We have weekly meeting and we present like this. If we want to focus one area, we have to review all paper, make the presentation, and find out the problem, what is the in this stage of problem, and how we can solve this problem. Well, in this case, we can play many and different antenna. You can use the wideband antenna. No need to put the dipole. But dipole also increase the height. We have like planar structure. You just put the normal patch here, wideband. You can reduce the size. This is also good. A confusion of in this area. So you can publish like this. They propose like this, you propose different way, conformal way. Antenna. Hemisphere conformal antenna for multi-band antenna.